already. So if I have the force of friction going to the left here, the object is going to roll to the left. Think about it in the yo-yo situation. So you can substitute the force of tension with friction. And if I pull this up, this guy's going to go up counterclockwise. So basically, I'm doing this vertical situation horizontal. That's why it goes left under friction. Same thing goes for tension. It's going to go right or clockwise under tension at R1 or R2, wherever it is. You can also imagine that this tension T could be pulling this object at the center of mass as if you're pulling just a point. As in the old school days, we're pulling this guy forward with tension T. We're accelerating it, and so therefore it's going to go to the right. So now we're going to take this same idea, the same tension with respect to this point, and it's going to roll all of these point masses towards the right. The center of mass is going to go to the right, and that pretty much dictates, or you should be able to see why this cylinder is going to go to the right in a clockwise fashion. The rotation would be clockwise. Be pulled to the right, but it's going to spin clockwise. That's the long and short of it. And that's why we get our torque equations like so. Any questions? Do we see that now? Just imagine that this is a vertical yo-yo. I pulled up with tension T. This guy is going to come upward, but clockwise. Now I lay it down horizontal, same thing. Clockwise torque, counterclockwise torque, boom, boom. Set up your equations, and we're ready to go. That okay? Yeah. See, torque is a vector that's going to either come out of the page or go into the page. The rotation is not the torque. That's the, that's the angular velocity of the object or angular acceleration. So torque is a function of the angular acceleration, right? Torque is not the spin, just to get to the root of your question. It's not the spin. It's a function of it. Oh, yeah, stop that. See? Like F equals ma. It depends on the acceleration. Or it produces, the net force produces an acceleration. So net torque, which comes in or out of the page, produces a net spin. So it's not the same. And yeah, so if you were confusing torque with spin, no. Depending on where this force is applied, like we had the pulleys, depending on where it's applied, we're going to produce a particular type of torque. So if I have my guy pulling down on this pulley here, this guy, if I have it attached to something, well, you got this pulley, so it's going to be spinning in a clockwise rotation. It's going to pull it down because torque is a function of both a moment of inertia and the angular acceleration, which is equal to those things. But do you understand the yo-yo illustration? That's the key, so that we can eliminate any type of illusion. Like taking this yo-yo, problem number 77, and apply it here horizontal. It's the same thing. Let me know if I've answered your question or you still need more clarification. Do you see that? Okay. Let me know yes or no. But the quick answer, no, torque is not the spin. Depending on how it spins, you know the sign of the torque. If it's a clockwise spin, negative, like here. Counterclockwise, it's here, positive. So let us continue on with this, because that's the most important part. We got to set up our torque equation, and then after that, we know that alpha is equal to linear acceleration divided by R2. Why is that? Because the net torque in the system is going to be applied at R2. Or better yet said, that since R2 is bigger than R1, and R2 is a function of this counterclockwise torque, the net torque is counterclockwise at R2. That's why it's A over R2 as opposed to A over R1 plus R2. Because T wants to make it clockwise, F wants to make it counterclockwise. Our net torque is going to be positive. And then we have our force equation, T minus F. T goes to the right, force friction is left, MA. Why is that? Why is it going to, be positive? Well, because the whole thing is going to be the linear acceleration is going to be pointing to the right. It's going to be rolling right. The center of mass actually rolls to the right. So that's why this is MA. And then we solve, get an expression for A, T minus F over M. Our second stage here. We were setting this up last time. So we substitute this into equation 1, FR2 minus TR1 equals I T minus F, which is A divided by R2. And I get this T minus F MR2. And then this becomes algebra at this point. So I want to get an expression for F. And it's going to be, just going to save some middleman. So I'll do some of this and distribute the I over here. And then it's, divided by R2 again. So it's going to be MR2 squared. Right? Because I did this to both everything. So then this is TR1. And this is going to be, so this is already, the common denominator is M. Yes, stop that. MR2, and then it's already divided by R2 again, so MR2 squared. And this is going to be multiplied by MR2 up top. Common denominator was MR2. Why are you so laggy with the dual pane? All right, let me just show that again. FR2 right? Because it's common denominator MR2, MR2. I don't want FR2, I want F. So I divide by another R2, and I get the squareds. But before I divided it by another R2, I multiply top and bottom here by MR2, which leads me to this. IT minus IF plus TR1 MR2 squared, and algebra 1 now. Okay, So I did a little something something here. I said F MR2 squared. And again, you can use your own method of simplification. At this point, it's trivial. The most important thing is those torque and force equations. You can use any simplification method that makes the most sense and can give you the same right answer. So MR2, it's multiplied by MR2 squared over here. And then I get all my force terms together, friction force terms. Equals IT plus TR1 MR2 factorization so you guys can see this okay? I mean, I was gonna do it earlier. I thought it was too small, but now to get the expression for FIT plus TR1 MR2. That's pretty much it. Factor out the T's. I plus MR1 R2 over M R2 squared plus I, and that's it. We prove, we show the expression works, or we show we get that expression. And then in direction of friction, I was just going to point to the left. It's kind of, that's supplementary to the whole thing. So yeah, friction points to the left. It's a rough surface. We're pulling it to the right. I have to go back over that. The linear acceleration is with it. The linear acceleration is from the center. So imagine that you're pulling T at the center. It's like a point mass. Think of that cylinder collapsed all of its matter into one point, black hole, and you're just pulling that point. It's going to the right. That's the linear acceleration. That's why it's MA. And another way to see that that's clockwise, pretty much like you look at the force that's pulling the object and see where the center of mass is going to point. And the center of mass is going to be pointing to the right. Therefore, under the influence of T, this thing is going to roll to the right. And that rolling to the right is a clockwise roll because the radius is going to do this. It's like you're pulling the yo-yo to you, like the friction case. I pull up, like number 77, this guy is going to go counter. Same thing with tension T, clock. I want to pull them up. And if center of mass is going to go straight up, but all of the mass points about the center of mass are going to rotate clockwise with regards to the center. And hence, again, that's why tension to the right produces clockwise. So hope you're all right with that. But any questions? Did I clear that up? All right, so we're going to continue on. If There are no questions. And we're gonna start angular momentum today. Okay, we've seen velocity, linear velocity. Now angular velocity is the velocity of a rotating object. Linear force, the rotational force, the torque. Linear acceleration, the rotational acceleration is, well, angular acceleration. Linear momentum, velocity, mass, P equals mv. And then angular will just be the momentum of a rotating object, angular momentum. So angular momentum is, we give it the symbol L because that's what's left. And since we're not rotating a point mass, we're going to rotate a collection of masses. So we're not rotating this center, we're rotating all of this, the sum of all of these masses that make up this object. So that means that we're rotating the distribution of all of these point masses from the center, meaning that we're rotating about the moment of inertia of this object. Because the moment of inertia is going to be the sum of all of these mass points from here. So instead of just point mass, we're distribution of mass that we say moment of inertia. Linear, not linear velocity, but angular velocity. So simply put, angular momentum is I omega. The rotational analog of this. And let's say that we started with our base cylinder, our basic moment of inertia expression, which would be mr squared. And we want to, basically we want to quantify these angular quantities, if you will, into like these linear quantities, mass, scalar, radius, scalar, the quantities that we're used to. And so we can rewrite angular velocity in terms of velocity times, or divided by radius. Why is that? Because if we were looking at a point mass on the extreme edge here, and we understand that the speed of this particle around this sphere is a linear speed, that's the tangential speed. The tangential speed is a function of its angular speed or angular velocity. Tangential velocity is radius times angular speed. And all the angular stuff is about the center. Angular velocity, torque, angular acceleration, angular momentum, all about the center of mass. And of course, we can have new angular quantities if we rotate it about some other point via the parallel axis theorem. We can now ascribe different quantities based on where we spin things from. But the simple case is to spin everything about the center of mass. So if we continue on here, this is going to be mass mr times v. And then technically, I'm not going to get into the cross product mathematics that you can see in section 1. You can read that if you wish, but for our purposes, I don't believe that we're going to need to divulge those too much, but this would come out to be r mv, or the radius across the linear momentum. And so that's the technical form of angular momentum. It's a new vector formed from the cross product of the radius and the linear momentum on the outside. So what else does that look like? So I'm just going to draw this picture and so stop for a second. So, okay, let's say that we had our center of mass here. I know it's an ellipse, but pretend it's a circle. So we have R. And let's say that we have a point mass out here that's rotating around the center, if that's the sun or something. And then it's got mass and it's got a tangential speed rotating around. Well, we know that the product of that is going to give us our linear momentum that we just call P. So radius cross P gives me my new L. So how do we know that the angular momentum in this configuration, this symbol here, this symbol means that the angular momentum comes out of the page? So again, we have to employ the right-hand rule to understand why angular momentum in this case points out. If you have your fingers represent the direction of the linear momentum around the circle, your fingers will be pointing up in the air. The radius will be the direction of your palm. So your radius should be pointing towards the left, your left. When you curl the fingers, P, about R, your thumb naturally points out. And so that's how you can visually comprehend that angular momentum comes out of the page. In this configuration, another configuration, it will be pointing into the page. If I had, say, the momentum over here, and now with respect to radius R, it's going to go into the page. So it just depends on the spin. Again, these new quantities are dependent on, well, the direction of those new quantities. It depends on how you spin the object. So if you spin it from the left here, angular momentum will go inside, and if you spin it from the right, it points on towards the outside or out of the page. Oops. If it rotates clockwise, it's negative. Of course. Absolutely. First principles. Yep. So again, your fingers represent the direction of momentum. Your palm is the radius. And there's other, right-hand rule logic that you can employ. And then the thumb would be the direction of L. The angular momentum. Any questions so far? Did we need to see something else? Re-explain? Am I going too fast? And be honest. We're all safe space. Oh, totally. Totally like torque, because all of those angular quantities are related because they're all coming from the center of the object. If I wanted to talk about torque, I will be looking at the force in the same direction as this momentum vector here times radius, and the torque would come out. In terms of momentum, angular momentum comes out. Regular velocity, angular velocity comes out. It just all. So it's like all the linear things are out here. Let's make sure that we can conceptualize. So V, A, the regular stuff from chapter 2 and 3, those guys are on the outside. The transformer here is the radius. This transforms the linear stuff into the angular stuff via the radius, because now we're going from a point mass to a collection of masses over a distance r. So it's just a transformation from these things to the new angular things. What in mathematics you call a transformer, something that create something else, transforms. So omega, L, torque, alpha, those guys are in the center, or from wherever you're rotating it from. Most of the time, to keep things simple, go to the center of the mass, and rotate from there. So yeah. So if this was force, radius, my torque comes out. So it has similar properties of torque, yes. Oops. Now, like force, what if the momentum is at some other crazy angle, because nature is weird, right? I mean, you can have it because a vector can be at an angle. What if P is directed see, so for an example, so let's say you have a P, this thing's so laggy. So I do this, whoop, theta. So all we do is we look at the component of the P that's perpendicular to a radius, which is P sine theta. So the general angular momentum equation is going to be L is equal to mvr sine theta. Yeah, so in terms of those quantities, so use component of momentum is perpendicular to R. It's going to be P sine theta. Or actually, technically, cross R. So it's going to be mvr sine theta. Okay. And of course, if theta is 90, it's just mvr. The sine of 90 is 1. And our last bit of today, start off Wednesday with an example. Okay. So just more of the concept. Okay, now we know that linear force, back in the day, we know it's a change of momentum over time, and so we can multiply time both sides, get the impulse. Calculus notation, same thing, dp dt. So then torque, then the torque that's going to be produced here. So you get a basketball spinning and it's just rotating, and then all of a sudden you put your hand on the outside of the basketball to get it spinning faster. You've created a torque because now you've applied a linear force on the outside to accelerate angularly, to accelerate the object, to speed it up, right? And so that torque is basically going to be a change in angular momentum in a certain amount of time, which is dl dt. These are equal, so of course we're gonna, be here. I haven't seen too many problems where you have torque times time. You can talk about an angular impulse or something like that, but the idea is the same. Because force times time, change of linear momentum, well, torque times time, change of angular momentum. In regular speak, this will be the stuff that's produced at the moment that you put your hand on the outside to speed the object up. Same thing goes when you hit an, let's say you hit a baseball into a wall, the time it takes for that impact is the impulse. Except that's on a line. This would be on a circle. Like, so if you imagine you have a wheel spinning and then you hit your hand on the outside of it, you know, you're going to cause it to rotate because your hand is going to want to go, well, the object's going to rotate. It's going to be spinning about the center. So that's basically it. Time for questions.